Hello and good afternoon, friends. Welcome to CEC Live Lectures. Dear friends, today we are going to continue further within our series on quantum chemistry. We would be discussing on quantization of translational energy particle inbox, and for this discussion we have with us in our studios Dr. Mehta Dua. Dr. Mehta Dua is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. Dr. Dua has immense experience and she continuously and persistently makes efforts so that she could easily reach to the students and their queries. Dear friends, we know you always have sets of questions which you believe to be answered by the eminent experts. So friends, as you know, we have today with us in our studios Dr. Mehta Dua, and if you want to ask questions from her on today's topic, then do call us through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. Friends, you're requested to call in the last 10 minutes of the lecture, that is from 4:20 to 4:30. Let's welcome our guest, Dr. Mehta Dua, and let's try to understand today's topic. Hello, ma'am. Welcome to the lecture.
So, hello and good afternoon to all my viewers. And today, again, I'll continue with the particle in a box, that is application of quantum mechanics. In the last few lectures, I have discussed about the postulates of quantum mechanics, what were operators, and now we will discuss how you will apply the quantum mechanics on certain systems. And today we'll start with the first application, that is particle in a box. So first of all is that is application of postulates of quantum mechanics. All the properties and the motion of a certain system, suppose we have a system whose mass is m and whose potential energy is v. For these kind of system, in fact for any system, the motion as well as the properties can be obtained from the solution of the well-behaved, that is fundamental Schrodinger equation. This we have already discussed, that is Schrodinger equation, and the derivation part we have done. So from this we have derived that all the properties could be derived, could be seen, could be explained with the help of this Schrodinger equation, and this is what we are going to do in the next lectures. Now, if you look at this Schrodinger equation, the Schrodinger equation, there are two variables which are present, that is one is mass m and the another is potential energy, that is v, which is present in the system. So, whenever we want to discuss about the Schrodinger equation, if we want to discuss about the properties, so we must know, first of all, we must know about the mass as well as the potential energy. So basically one system, it differs from another system on the basis of the mass as well as the potential energy, and thus whenever we want to find out the solution of Schrodinger equation, which will ultimately give you the properties of the system for different system, just by varying the mass and the potential energy. So by this way, so in other words we can say that whenever we pick up different systems, the only thing which we want initially is that is the mass as well as its potential energy. Now, so we can find out the exact solution of this Schrodinger equation. For very simple system, it is very easy, that is you can find out the exact solution. But for the complicated system, that is which is containing like multi-electron system, like if we can take an example of helium where there are 2 electrons, it is very difficult to solve this Schrodinger equation, and for that we have to apply the approximate methods on the Schrodinger equation. This is the part which we will do later on, which after we have done a number of simple system, like because in my series of lecture first we will discuss particle in a box, hydrogen atom, or rigid rotator or vibrator, and when all these things get finished, then we will go to the approximate method, that is the multi-electron system or the complex system. So, for the simple systems, exact solution of Schrodinger equation can be obtained. Now, before discussing the particle in a box, that is the simplest system in the case of quantum mechanics, first I want to tell you that what are the various steps which are involved. What are the steps which a student should apply, should take into consideration, that how to solve a particular system. There are certain steps. So the first step you can see on the slide I have given in the form of points, that is step 1, 2, 3, 4. Just see that first of all we have to write the generalized Schrodinger equation. And for this, what is Schrodinger equation? Schrodinger equation is H psi E psi. And I have already told you that what is H operator. H operator is the Hamiltonian operator, that is the total energy in terms of quantum mechanics, and H operator is T operator plus V operator. So this is my Schrodinger equation, and we have to first write the generalized form of this equation, that is in general what could be the potential energy, what could be the potential energy and kinetic energy of the system, and write the Schrodinger equation. So according to quantum mechanics, microscopic particles, it is never at rest. So kinetic energy is never equal to 0. But yes, potential energy can be 0. So the first we need to define the potential energy. So whenever a problem comes to a person, first of all, he or she must know that what is the potential energy of the system, because in some cases it could be 0 and in some cases it could not be 0. So the first thing is that a student should know what is the potential energy of the system. This is the thing which has to be clarified initially, and because there is always some kinetic energy of the system, but the problem is whether it has got some potential energy or not. Now the second is, once we have written a generalized Schrodinger equation, then we have to solve that Schrodinger equation, obviously to get the wave function as well as the energy. By solving the Schrodinger equation, always initially we get the wave function as well as the energy, and once the wave function of that system is obtained, then we can calculate the number of properties of that system. So the basic thing, the most important thing is to obtain the wave function. And to obtain the wave function, first of all, we have to write the generalized form of the Schrodinger equation. And how to write the Schrodinger equation? That is H psi E psi. What is H operator? H psi E psi, and H is the H operator. And what is the total Hamiltonian operator? It is T operator plus V operator. I am again repeating the same thing. And T operator can never be 0, because most of the time the microscopic particles, according to quantum mechanics, quantum is actually the study of the moving particles, the small moving particles. So kinetic energy can never be 0. So there is some value of T operator, but yes, it may be possible that V operator, it may become 0, which you have to check whether it is 0 or not. Depending upon the system, it varies. And then once you have write the basic Schrodinger equation, then the boundary conditions are given. The boundary conditions are given, that like a rotator, what are the boundary conditions? Like if a particle is moving, a particle in a box, a particle is moving, and what is the length of the box? That would be the boundary conditions of the system. Then we have to apply the boundary conditions onto what? Onto the basic Schrodinger equation which we have written to calculate the constants which are present in the Schrodinger equation. So first you have to write the generalized Schrodinger equation, and then we have to apply or specify the boundary conditions which are given. And then once the constants are obtained, then you can obtain the value of psi. And all these things you can see in one of the simple system which I'll discuss today, that is particle in a box. These steps you can see easily, that how first I have written the generalized solution, how by applying the boundary conditions I have calculated all the constants, and then I have derived the expression for the wave function as well as the energy. And once the wave function is obtained, by using the wave function we will calculate the value of the other properties. And I have already discussed in the postulate of quantum mechanics that how will you calculate the properties of a system. That is, first is the eigenvalue equation, that is A psi and then small a psi, and by this the exact value is obtained. In case some of the properties are not calculated by using the eigenvalue equation, we can apply the mean value theorem, which will give you the most probable value of the property. So this is how these are the steps by which you can apply, by which you can solve certain systems. Now in this case today we will discuss the most important, that is the simplest motion of a particle, that is the translational motion of a particle. the most simple system of motion that a particle can have is the translational or the linear motion. In general, the translational motion is the kinetic motion of a particle. So here today we will deal with the linear motion of a particle under quantum mechanical. We are discussing two types, that is under the bound state, that is applying, that is boundary conditions, as well as under the free state, that is without boundary condition. Now, the quantization of, because ultimately we will calculate the wave function as well as energy from the system. So this is the like today we are discussing about the translational motion. After completing the translational motion, we will jump upon the rotational motion of the particle. Then we will discuss about the vibrational motion of a particle, like this, the electronic motion, the nuclear motion. These are all the things which we have to discuss under quantum mechanics, and today I have picked up the simplest motion, that is the translational motion. Like you can say the to and fro motion of a particle. A particle is just moving to and fro in a bounded state. This is what we have to discuss today. Now the quantization of translational energy, the same topic we have also discussed in the classical mechanics. Like translational motion, like electron, it jumps on the various electronic energy levels in an atom. What Bohr has discussed, that is translational motion of the electron. It jumps from one state to another. So the simplest application of Schrodinger wave equation. So this is the simplest thing which we are discussing or which we are taking today. That is now, according to classical mechanics, the energy of a moving particle can vary continuously, that is it can have any value. There is no restriction on the values, that is a particle can have any value. But according to the quantum mechanical results which are obtained from the solution of Schrodinger wave equation for the translational motion, we can explain that the values are not quantized. It is not seen that it is continuously varying, but the values are quantized, that is it can only have certain discrete values, that is only some of the values are allowed for a molecule to translate, that is there is some restriction. Now this is the best example for the translational motion which I am going to discuss, that is particle in 1D box. Now further I will also show you the diagram. The particle in a box model, it serves as the simplest case. Now before discussing this particle in a box, I just want to tell you that there is nothing like particle in a box. Actually this is it is just an imaginary system which we are discussing today, because the results, this system is given to explain that how you can apply quantum mechanics on a particular system, just to show you that how quantum mechanics can be applied, what are the different methods what we are applying, and then after few lectures we will take the actual systems like rigid rotator or vibrator. These are the systems, but particle in a box is an imaginary system. There is nothing like particle in a box. So particle in a box model, it is just a model, imaginary model, and it serves as the simplest case for the treatment of bounded electrons, as if you can like the particle is bound in a box, just like electrons in atoms and molecules are bound to the nucleus and they are revolving around the nucleus. Just like in this particle in a box, the electron is just moving to and fro, to and fro, to and fro. It is just bound in a box. So you can compare it with an bounded electron like particle in a box. So particle in a box model, it serves as the simplest case for the treatment of the bounded electrons in atoms and molecules. It is a hypothetical case. I have already told you it is just an imaginary model in which we assume that a single particle whose mass is m is restricted to move in an imaginary one-dimensional box whose length is a, with an infinitely high walls at the two ends. So it is a box which is length is very high, that is it is very long, and the boundary conditions are, and what is the length of the box is 0 to a. Now as long as the particle, one thing which you have to keep in mind is simply that as long as the particle is inside the box, its potential energy is 0, and when it is on the walls of the container or outside the box, it is infinity. The simplest thing which a student should remember, that as long as the particle is inside the box, we assume the potential energy, that is V equals to 0. Now, which implies that is it is not gaining any height, its potential energy, because potential energy is mgh. So its potential energy is 0, which implies that particle is free to move inside the box, that is particle is not under any external force and its potential energy does not vary inside the box. And in order that the particle may remain inside the box, because actually we are discussing about particle in a box, so obviously we want that particle should remain inside the box and does not move outside the box, otherwise there would be a contradiction, otherwise it will become outside the box, because we are discussing inside the box. So it is essential that the potential energy outside the box is very high, that is which is equal to infinity. So as soon as the particle reaches the wall, it is reflected back. Why? Because there is a lot of potential difference between inside as well as outside. So due to high potential energy, and thus particle is just confined to move in a box of length a. So in simple words we can say that there is a box whose length is, you can see the diagram, it's very clear from the diagram, whose length is from 0 to a, and it is very much high, the walls of the containers are very high, and when the particle is inside the box, potential energy is 0, and when the particle is on the walls or outside the box, its potential energy is infinity. Now, in fact, 1 minute before, only 5 minutes, I have told you that how to apply, how do we start? The first thing is that we have to write the Hamiltonian for that system. And what is Hamiltonian? Hamiltonian is kinetic energy as well as the potential energy. So what is kinetic energy operator? Because we are discussing quantum mechanics, so we have to write everything in terms of operators, and our kinetic energy is minus h cross square upon 2m. M is the mass of the particle, we have already taken, into del square, that is the Laplacian operator, plus Vxyz. So this is the Hamiltonian operator. Because we are discussing particle in one dimensional box, so we won't take y and z, we will simply take the x factor, because I am taking the length of the box, let it be x, and its limits are from 0 to a, the x is from 0 to a, that is the length of the box. Now if we take a particle in one dimensional box which is moving in x direction, where the limits in x direction are from 0 to a, so the Hamiltonian could be written as h operator minus h cross square upon 2m del square by del x square. I have removed that y and z part because I am taking a particle in 1D box and my 1D is x direction, plus Vx. Now we have to write the Schrodinger equation. The first step, how to apply the quantum mechanics on a certain system, the first thing is we have to write the Hamiltonian. From the Hamiltonian I have to write the Schrodinger equation. Now my Schrodinger equation is h operator psi E psi. Put the value of h operator, this will become in the brackets minus h cross square upon 2m del square by del x square plus Vx bracket close psi equals to E psi. Now this you can see on the slide, this is clearly given on the slides. I am doing the derivation part, that how we will derive the energy as well as the wave function. So first is Schrodinger equation when the particle is outside the box. We have to discuss two cases, that is outside the box as well as inside the box. Ultimately we will solve for inside the box because system is actually inside the box. So Schrodinger equation when the particle is outside the box. Now outside the box I have already told you that potential energy is infinity. So simply put potential energy, that is V equals to infinity. It will become minus h cross square upon 2m del square psi upon del x square plus infinity psi equals to E psi. Now take both the things, that is minus h square as well as infinity part, on the right hand side. So you can see it will become positive sign h cross square upon 2m del square psi del x square, because I am taking on the other side, that is why negative sign has disappeared and it has become positive, and in fact infinity would also become minus infinity. So taking psi common, it will become, the second expression you can see, E minus infinity psi equals to 0. Because energy is very much, any value is obviously very much less than infinity, and therefore neglecting energy in comparison to infinity, so the above equation becomes, that is simply the E factor would vanish. So it will become h cross square upon 2m del square psi del x square, because E is going to be finished, so we are left with minus infinity psi equals to 0. Dividing, now I'll divide the whole thing by h cross square by 2m. So it would become del square psi del x square, because I'm dividing. So minus 2m upon h cross square, infinity psi equals to 0. So now because it has become 0, now anything whenever it is multiplied by infinity, the whole thing would become 0, everyone knows this. So it will become del square psi del x square minus infinity psi equals to 0. I am taking infinity psi on the right hand side. This will become del square psi del x square equals to infinity into psi, and when I solve for this psi, so it will become what? 1 upon, I am just rearranging the things. Psi will become 1 upon infinity del square psi del x square, and anything, whenever anything is divided by infinity, it will become 0. So psi comes out to be 0. So when I solve the Schrodinger equation for a particle on the walls as well as outside the box, the wave function comes out to be 0. So the only solution possible for the Schrodinger equation when the particle is outside the box, as well, I am mentioning over here, as well as on the walls of the container, psi equals to 0, and this proves that outside the box as well as on the walls, psi equals to 0, which implies that the particle cannot exist on the walls as well as outside the box. So when x is less than equal to 0 and greater than equal to a, particle cannot exist. Now second, that is Schrodinger equation when the particle is inside the box. Whenever the particle is inside the box, our potential energy is 0. So the Schrodinger equation, which we have already discussed, this will become minus h cross square upon 2m del square psi del x square plus 0. In the first part we have taken this as infinity. Now in this part I have taken this as 0. So it will become 0 psi equals to E psi. Now this will become, because 0 has vanished, so we are left with minus h cross square upon 2m del square psi del x square equals to E psi. Now again I am taking the negative part, that is minus h cross on the right hand side. It will become h cross square upon 2m del square psi del x square plus E psi equals to 0. I have simply rearranged by making potential energy 0. Similarly, like in the first part also, I have divided the whole thing by h square by 2m. Here also dividing the whole expression by h square by 2m. So it will become del square psi upon del x square, because I am dividing, so it has been vanished. It will become 2m upon h cross square E psi equals to 0. Now to solve this equation, it is a differential equation, and again to simplify this, I am taking 2me upon h cross square as a constant, that is k square. So I have simply put it 2me upon h cross square equals to k square, and k square is a constant. So the above Schrodinger equation which we have with us, it will become del square psi del x square plus k square into psi equals to 0. So our first step was to write the Schrodinger equation. Now once we have put it the value of the kinetic energy as well as the potential energy, and we are obtained, now we have landed up to a second order differential equation which you can see on the slide, that is which is containing k square equals to 0. So it is a second order differential equation, and to solve this we have to find out the general solution of the wave function. And the thing is, that is the nature of wave function. It should be such that if the wave function is differentiated twice, then we must back the wave function multiplied by a constant. So actually that what is after solving the Schrodinger equation, what is the thing which we want? That is a wave function. So we have imaginary, that this is a imaginary, like a hit and trial method. Okay, if we solve this equation, then what would be the wave function which we are land up to? That is our wave function is a sin kx. So let the general solution like in differentiation we do in mathematics, similarly we are applying here. So that is for the second order differential equation, let the general solution of this differential equation is psi equals to a sin kx plus b cos kx. Now if you see this equation, there are three constants which are unknown, that is capital A, capital B as well as capital K. So these are the three unknowns with us, which first we have to find out. Once A, B and K is known, then we can calculate the energy as well as the wave function. So A and B are the constant. Now obviously we can have many values of A, B and K, and by that we can have many values of psi also, but this is not true. So depending upon the values of A, B and K, psi can have many values obviously. But the thing is, all the values, again what we have discussed, that all the wave functions are never ever acceptable. There are only few wave functions which are acceptable, which are known as eigen wave function. And the most important thing is, which satisfy the boundary conditions. So now the first thing is, now our motive is to how to calculate A, B and K. So once the general solution of psi is obtained, now the thing is that how will you calculate the wave function? How will you calculate the value of A, B as well as K? So now we will apply the boundary conditions. Now what are our boundary conditions are? That is, the length of the box is 0, so the value of x is 0 to A. And when x equals to 0, psi equals to 0. And when x equals to A, because on the walls, I have already showed in the diagram that on the walls the wave function is when the wave function is 0. The first part we have already discussed, that is on the walls as well as outside the box, the wave function is coming out to be 0. So when x equals to 0, psi equals to 0. When x equals to A, then also psi equals to 0. So when I apply these boundary condition on the wave function, first you can see that when x equals to 0, psi equals to 0, by putting these values, that is x 0 and psi 0 in the expression of psi, b comes out to be 0, and we are left with A equals to A sin kx. And similarly, when we apply x equals to A, psi equals to 0, we are left with, that is b equals to 0, and then by this we can find out the value of k. So this we will discuss after the break, that is the boundary conditions as well as the calculation of wave function as well energy. Thank you.
With this note, thank you ma'am, thank you so very much for giving us this session. Friends, we would be meeting again shortly after this break. Hello friends, welcome back in this session, and in this session we are going to talk on the derivation which we have discussed in the previous session. Also we would be continuing further and would be understanding the derivation of particle in a box, and for this discussion we have with us in our studios Dr. Mehta Dua. I would like to request Dr. Dua for explaining further. Welcome back.
Okay. So in the first session I have discussed about how we have land on to the general solution of the wave function for a particle in a box. So once the general solution, that is the expression for the wave function, is obtained, that is psi equals to a sin kx and b cos kx, now we have to calculate the constants which are present in the wave function, then only we can get the exact solution, that is the wave function for the particle in a box. Now how will you obtain the value of a, b and k? And once a, b and k are obtained, then we can get the exact value, that is the expression for the wave function as well as energy. The first thing is that what are the things which we have with us, that is the boundary conditions. So first of all we will apply the boundary conditions on this wave function. Now for the wave function for the particle in a box, the boundary conditions are, that is the values of x are 0 to a. If I take x equals to 0, at that time psi equals to 0, and when I take x equals to a, at that time also psi equals to 0. Why? Because in the diagram of particle in a box I have already shown you, that is whenever the particle is present outside the box or on the walls. On the wall means x equals to 0 and x equals to a. On the walls the wave function is always 0, that is particle does not exist on the walls. Now if I impose this boundary condition, suppose my first boundary condition is x equals to 0, psi equals to 0. Now what is my expression? Psi equals to a sin kx plus b cos kx. Now put the value x equals to 0 and psi equals to 0. So my expression would be 0, psi 0, a sin 0 plus b cos 0. Now sin 0 is, I have already told you, you can see that sin 0 is 0 and cos 0 is 1. So we are left with a into 0 plus b into 1. So by this what happens? That b becomes 0. So what is our expression we are left with? That is a sin kx. Now out of a, b and k, our b has become 0. Now the thing is, what is the value of a as well as k? Now we will apply the second boundary condition, that is when x equals to a, psi equals to 0. This will become psi is a sin kx and b cos kx. Now I apply the second boundary condition. Instead of psi put 0, a sin ka, and this will become b cos ka, and b is already 0, so it becomes 0 into cos ka. So by this a second term will get cancelled out, it will become 0. Now we are left with a sin ka equals to 0. Here a cannot be 0. Why? Because if a becomes 0 and b is already 0, then wave function will vanish. And that is not possible, because if a particle is there, if a system is there, then the wave function, that is storehouse of information, must be there. So a cannot be 0, because if both a and b will become 0, then psi will also become 0 at all. So thus for this, what is the thing, that is sin ka must be 0. For sin ka to be 0, what would be the values of sin so that it take up the value of 0? All the n pi multiples of sin, they have 0 value, like sin 180 degree, like this. So sin k is 0, instead of 0 I will put sin n pi, because all sin n pi's have got value 0. So sin gets cancelled, so we are left with ka equals to n pi. What is k? K will become n pi upon a. So this is how we have obtained the value of k as well as b. So by applying the first boundary condition, I got b equals to 0. By applying the second boundary condition, I got the value of k, that is n pi by a. So again my generalized solution of wave function, it becomes a sin ka. Instead of k, put n pi by a. So it becomes psi equals to a sin n pi by a into x. Now the thing is that again we are left with a constant a. Still we doesn't have the value of a with us, and if a constant is left, then how will you get the exact solution of the wave function, the expression of the wave function? To get the exact solution, we have to be rid of with all the constants we have used. So how can you calculate the constants value? That is, the first thing is that you can apply the boundary conditions, and even after applying all the boundary conditions, all the constants are not calculated. Now what is the next thing to calculate is, that is normalization of the wave function. I have already told the kinds of the wave function, that is orthogonal wave function, the orthonormal wave function, the normalized wave function. These were the things which were already discussed to make the base, because now those things will help you in solving the different systems. So this is the normalization of the wave function. By this expression for the wave function, it contains the undetermined constant a. This is what I am telling you, that it contains a and its value has to be obtained by the process of normalization. And now what is the condition of normalization? That is integrating minus infinity to plus infinity psi star into psi d tau equals to 1. This is the condition. Now because we have only x with us, so obviously instead of d tau we will use dx. Because there is nothing like iota, that is imaginary part, which is present in wave function, so our psi and psi star will remain the same. So it is a sine n pi x by a into x. Now put the value of psi and psi star in the integration. Just see, this is simple, and please learn this derivation very clearly. Why? Because the same derivation will be used in many chapters. The same derivation will be used at many places. So just concentrate. That is because we have boundary condition from 0 to a. In generalized form, we always write minus infinity to plus infinity, that use whatever you have. Because now in this case, our boundary condition is 0 to a. Now what is my psi and psi star? Both of them are same, that is a sine n pi x by a and a sine n pi by x by a. Instead of d tau, I have used dx. Why? Because it is in x direction, that is Bundy box equals to 1. So this becomes a, because it is a constant, so it becomes a square sine square n pi x by a into dx. Now we have put we have sine n pi x by a. Now to again simplify more, I'll put n pi x by a equals to y. So now differentiate both the sides, because if I'll replace that thing by y, then obviously dx has also be replaced by dy. Otherwise how will you do the derivation, the differentiation? So n pi x by a equals to y. Now I'm differentiating both the sides. This will become n pi by a, x will become dx, y will become dy. So what would be my dx? It would be a upon n pi into dy. Now using the boundary conditions, because if I have converted all the things in terms of y, the constant, I have taken n pi x by a into y, I have taken dx in terms of y, then obviously boundary conditions, which were the conditions in terms of x, has also be converted in terms of y. So when x equals to 0, then what would be the value of I? I have a expression which is in the first term of this slide, that is n pi x by a equals to y. So when I put n pi x by a equals to y, when I put x equals to 0, then y will become 0. If I put x equals to a gets cancelled, y becomes n pi. So instead of the boundary condition 0 to a, now we have boundary condition 0 to n pi. So now again coming to the same derivation, just see the slide, I have come to the same derivation. Therefore the above integral, my integration will become what? I have already a square, just see on the slide, 0 to n pi, I have changed the boundary condition, sine square, instead of that constant I have put it y, and instead of dx I have written a into n pi into dy. So everything has been now changed in terms of y equals to 1. Now I am taking a upon n pi constant, that is outside the integration. It will become a square a upon n pi, and within the integral we are left with sine square y dy equals to 1. Now you can see on the right hand side in a bracket I have written, that is, this is the formula which is used in integration, simple formula in the trigonometry part, that is 2 sine square y is 1 minus cos 2y. So sine square y would be what? 1 minus cos 2y divided by 2. Just I am taking 2 in the denominator part. So use this expression and solve the integration. Instead of sine square y dy, because we haven't got any formula for sine square y, so how you will solve this sine square y? This will become 1 minus cos 2y divided by 2. I am telling you in the brackets so that no one gets confused in solving this expression, that how will you get sine square 1 or all of a sudden it gets converted into 1 minus cos 2y. So that is why I am telling you that this is the formula which I am using, and sine square y is getting converted into 1 minus cos 2y divided by 2 dy equals to 1. Now simply we will integrate. I am taking 2 outside the box, outside the integration in fact. So we are left with 1 minus cos 2y dy equals to 1. You have to solve this integration, that is, first I will integrate 1 and then I am integrating cos 2y and then applying the boundary condition. By integrating dy I get y. By integrating cos 2y, I will get sin 2y. In the integration constant also, you can also see a constant in the division, that is in the denominator. So it will become sin 2y by 2. Now I will apply the boundary condition, that is 0 to n pi. The constants are there as such. First put n pi value, this is n pi minus sin, because it was 2y, so it will become 2 n pi by 2 minus, again putting the 0 value, this will become 0 minus sin 0 by 2, because 0 is 0 and sin 0 is already 0. So this will become vanish. And one thing more, that is sin 2 n pi, 2 pi's, all 2 pi's is also 0. So all the things are becoming 0. So only one thing is left, that is n pi. So the expression will become a square by a 2n pi in the brackets n pi equals to 1. N pi gets cancelled. So we are left with a square into a by 2 equals to 1. So a square equals to 2 by a. And we are left with, that is, a will become under root of 2 by a. So by this we have got 3 values of constant. First, by applying the boundary condition, by applying the first boundary condition, I got the value of b, which comes out to be 0, and then by applying the second boundary condition, I got the value of k, that was n pi by a. And now by applying, because if even after applying the boundary conditions you are left with some constant, then we have to do the normalization part, and when the normalization of the wave function is done, we are obtained with the constant a, which is found to be under root 2 by a. So once all the constants are obtained, then you can write the actual expression of the wave function. My wave function was a sin n pi x by a. My constant value a, which I have obtained by normalization, is under root 2 by a sin n pi x by a. Now what is so this is the final wave function, this is the final expression of the wave function which we have obtained for the particle in a box. What is the unit of wave function? This is a very important question which usually students get to see in their exams, that what is the unit of wave function for the one dimensional box. Now you can see that ultimately we have only a with us. That is, what is a? A is length, which could be in centimeter or meter, and it is in the denominator. So this way, and it is in under root, that is under root 2 by a. So this becomes centimeter to the power of minus half, and dimensions would be obviously L, that is for the length to the power of minus half. Now because I've already told you that is after solving the Schrodinger equation, first we will get two things. One is the expression for the wave function which we have obtained, and also the energy at the same time. These are the things which we can get directly from after solving the Schrodinger equation for any system. Now the thing is that how will you calculate E, that is energy? We have already put it that constant, that is k square equals to 2me upon h cross square. Now from this, what is E? That is k square. Otherwise, why should I calculate the value of A? The only thing why we are forcing upon that we have to calculate the value of constant k just to get the value of E. Similarly, we are forcing upon to get the value of A and B to calculate the value of psi, because we want the value of psi. So in every system, first we have to write the Schrodinger equation, and by the Schrodinger equation we directly get the wave function as well as energy, and then by using the wave function we can get the other properties of the system. So now k square is 2me upon h cross square. So by rearranging, E equals to this will become k square h cross square divided by 2m. Now what is my k? K is n pi by a, and then squaring. H cross is h upon 2 pi. These two things I've shown in the bracket in the front of this expression, that is k equals to n pi by a and h cross is h upon 2 pi. And then 1 upon 2m. So when you multiply this thing, we'll get the equation n square h square upon 8ma square. So the equation number 1 and 2, they are the solution of the Schrodinger wave equation for a particle in one-dimensional box. I am telling again and again, from the Schrodinger equation, one will always get, on solving the Schrodinger equation, one will get the value of the wave function, not the value, in fact the expression of the wave function and the value of energy. Now we will discuss about some of the conclusions from the study of the particle in a box. This I have discussed in certain points, like first is quantization of energy. In the classical mechanics, according to classical mechanics, energy of any moving particle, in fact a small particle, it varies continuously. It doesn't have a fixed value, it varies continuously, it can have any value in fact. But from the solution of Schrodinger equation of a particle in space, we can explain that no, they are not varying continuously, they cannot have any value of its own, but the values are quantized. Quantized meaning they are restricted, that yes, you can have only these values, not more than that. So you can have only discrete values, because in quantum mechanics, just you have seen that what is the expression? The expression is n square h square upon 8ma square. So by the time you by putting the values of n, you will get the value of energy. So in this expression, since n can have the integral values, n cannot be 0.1, 0.2, 2.3 or 2.4. So they are not allowed. So obviously any energy value cannot be allowed. Only certain values are allowed. So in this expression, since n can have integral values like 1, 2, 3, etc., it cannot be 0, not at all 0, and therefore energy associated with the motion of a particle in a box can only have the discrete value. And thus it is concluded that whenever a particle is confined to move in a limited place, the energy is quantized, because like in Bohr model, there was no restriction on movement of electron. Electron can go to any level, anytime, any level. But here quantization said no, that is not possible. It can go only up to certain distinct level, only up to certain discrete levels the electrons are allowed. Now second, one thing more, that n cannot be 0, because in case our n becomes 0, if n becomes 0, then the exact position of a particle can be defined, and exact position cannot be defined according to the Heisenberg uncertainty principle. So in case n equals to 0, then the exact position could be defined, and which violates our Heisenberg uncertainty principle. According to Heisenberg uncertainty principle, or microscopic, for the microscopic particles, exact position and momentum cannot be determined at the same time. Also, microscopic particles cannot be at rest according to the postulate, because quantum is actually the movement of the microscopic particle. If the particle is not moving, then how will you study under the quantum mechanics? So n cannot be 0 again. Again, third point which is helping to explain that n cannot be 0, that is, in case n equals to 0, then energy will be 0, and if E is 0, then psi will also become 0. So this is not acceptable, because psi is the storehouse of information, which cannot be 0 at all, because if psi becomes 0, then everything will become 0. Now, what is 0 point energy? 0 point energy, please do not be in a confusion that 0 point energy is the zero energy, that value equals to 0. 0 point energy is actually the minimum energy which a particle or a system could have. So the 0 point energy of a particle in a box is not the value, it doesn't mean that E equals to 0, it is the lowest energy of a particle in the box, that is the minimum value, and it can be obtained by putting the minimum value, and minimum value can not always 0. So the minimum value that n can possesses in this case is 1, and therefore the 0 point energy is E1, that is, by putting n equals to 1, it will become h square by 8ma square. So the lowest value of energy, so what is the 0 point energy? The 0 point energy is the lowest value of energy, which is h square by 8ma square, and this shows that particle is never ever at rest. Even at absolute 0 it is moving with a very low kinetic energy, but yes, it is moving, and thus the particle in a box will continue to move in a to and fro motion. This is the translational, it is continuously moving like this, that is to and fro in the region 0 to A, even if the temperature is at 0 Kelvin. So the particle is never ever at rest in a particle in a box. So by this, the exact position, because it is always moving, so the exact position cannot be determined, and obviously momentum can also not determined. So the 0 point energy is in accordance with the Heisenberg uncertainty principle. Now the next thing is that we have, what are the allowed energy levels? How can you draw all these things in a diagrammatic form? How can you show that it is moving? So these are the different energy levels in which a particle in a box can move. You can see that n equals to 1, what the energy would be E1. When we put, that is, when it moves, that although it is moving to and fro, but when it moves, gradually its energy increases, that first of all it was in n equals to 1, and then it will go n equals to 2. Like when we do skipping, the movement of the rope suddenly, in fact gradually it increases. This is the thing. So the allowed energy levels are shown on the horizontal lines we have shown, that is n equals to 1, then 2, then 3, and then 4. So this is the energy level of a particle in one-dimensional box. These straight horizontal lines shows that energy of the particle is same, that when the particle is present, suppose if a particle is present in n equals to 1, so wherever it is present on this line, its energy is same. This shows that for a particular value of n, suppose we have a value of n, the energy does not change with x, that when it is moving in to and fro motion in a particular level, its energy is same at any point when it is in n equals to 1. Since energy, it is independent of time, thus the system under consideration is a good and simple example of the conservative system, because it is independent of the time. Now the next is, let the energy gap, suppose now we have discussed about energy, that what is the expression of energy, what could be the values of n in energy, that is n can never be equal to 0, and then we have discussed that why it can never be 0. If in case it becomes 0, then what will happen? And then I have shown the energy diagrams. Now one thing more we can discuss, that let the energy gap. Now we have to discuss the energy gap between the energy levels. That is, suppose I have a level n, and then the successive level is n plus 1, that is final as well as initial. So this becomes n plus 1 square h square upon 8m square. I have simply put it n and n plus 1 in the expression of energy, and suppose the electron is jumping from n to n plus 1 level. Now what would be the formula? That is n square plus 1. I am just applying a square plus b square plus 2ab as simply. So this will become n square plus 1 square plus 2n minus n square. So we have 2n plus 1 h square by. So by this we have calculated, even you can calculate directly, you can calculate the energy of each and every level and then take the difference, or by this you have calculated the formula for delta E, that is 2n plus 1, and n is the lower value. So this will become, these are the energy differences of the various energy levels. So in the next lecture we'll continue with the same topic, that is particle in a box. In fact, I'll continue with the conclusions, and we will also do some numericals based on this topic so that it would be more clear to all of us. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us a productive session. And as Dr. Amita Dua herself said, that we would be continuing further on particle in a box in our forthcoming sessions. So friends, keep watching us and keep writing us. To watch us the number of times you wanted, you can just log on our YouTube channel. Our YouTube channel is www.youtube.com/CEC-EDUSAT. This is where you can log on and see number of lectures on various subjects. Friends, we would be meeting soon and would be discussing further. Till then, take care. Goodbye. Thank you, ma'am. Thank you once again.